Okay, welcome everyone. So we just took a look at a more standard type of vector space, namely R2 with our usual operations. I want to take a look at less standard vector space where now our objects are no longer vectors. So here we're going to take our set of objects V, going to be all polynomials. I'll denote this P2 that have at most degree 2. So we're going to call these degree 2 polynomials, but I will consider linear polynomials as well as constants to be a degree 2 polynomial. So I'm trying to say that if I had something that looks like f of x is equal to 0, x squared plus 0x plus 7, I'm going to consider this as an object inside of V because its degree is at most 2. So we're going to consider all of these objects of this sort of form where I have some constant times x squared plus some constant times x plus a constant term over here. And these terms may or may not be 0. So the degree could be 2, it could be 1, or it could be a degree 0 thing. And we're going to define usual operations, meaning that if I have two quadratics and I add them together, then we add the like terms together. And if I were to try and multiply a quadratic by a scalar, then we distribute that scalar to each term in the quadratic. So those are our two operations. And let's now consider whether or not this is going to be a vector space. We need to check whether these two operations satisfy our properties, and we have 10 of them. So what we can see here is if I take some arbitrary quadratic, a2x squared plus a1x plus a0, plus some other quadratic, b2x squared plus b1x plus b0, what do I get? Well, I would add the quadratic terms, so I get an a2 plus b2x squared. I would add the linear coefficients, so I have a1 plus b1 times x. And then I would add the constant terms to give me an a0 plus b0. And what's left over is something that looks like some constant times x squared plus some coefficient times x plus some constant term over here. So this is closed under addition. When I add two degree 2 polynomials, I get something that is going to have at most a degree 2. We can quickly verify as a result of addition being commutative that if I take f plus g, I'm going to get g plus f. This is true no matter what these functions are. Certainly it holds for degree 2 polynomials. And the same goes for the associative property of addition. These properties all follow from the fact that that is how addition of the coefficients is going to satisfy these properties. For the 0 vector here, the 0 vector in this case would be the polynomial that is 0x squared plus 0x plus 0. So our 0 vector here is just the polynomial f of x is equal to 0. And for any quadratic f of x, it's going to have an additive inverse where we just take minus 1 and multiply each of the coefficients. We change the sign of those coefficients. So now if I took f of x and I add to it minus f of x, we get back 0x squared plus 0x plus 0, which is how we define the 0 vector. So we do have additive inverses here. And continuing with the other properties, if I take any scalar c times a function, a quadratic function, then I get c a2x squared plus c a1x plus c times a0. And this is a polynomial that is going to have at most degree 2. We can certainly distribute c through addition in this way. Again, this property is really just going to follow from properties of regular addition and multiplication. This distributive property, when I'm taking the sum of two scalars times a quadratic f of x, certainly that is going to equal c times f of x plus d times f of x. So these distributive properties hold. We can multiply d times f of x and then multiply c, scalar c, or we can first take the product of scalar c and d and multiply by this quadratic f, and these two ordering of these operations will give us the same result. And then lastly, yes, if I take any quadratic expression and I multiply it by 1, I get back that same quadratic expression. So we have a multiplicative identity. So here we have a slightly more abstract looking set of objects. We're not talking about vectors in R2 or R3, but we're talking about all polynomials that have at most degree 2. So even these weird looking objects, polynomials, if we define addition and multiplication, scalar multiplication in this kind of typical way, then this set of polynomials along with these operations, that would satisfy the axioms for a vector space. So here is another example of a vector space.